So in this video, we will spend some time talking about problem number 2. This was from the 2017 AP Calculus BC exam. It's a calculator question that involves polar curves. And so if we get right into it here, we have two polar curves. R equals f of theta is going to trace out this inner curve right here. And then R equals g of theta is going to trace out this outer curve. They tell us that the range of values for theta we're concerned with are 0 up to pi by 2. They define two other regions. They say region R is going to be the region that's in that first quadrant, bounded by the x-axis and f of theta. So you see region R right here. And then S is going to be the region in the first quadrant bounded by the two curves, f of theta, g of theta, and the x-axis. So region S is everything that you see right in this space right here. In part A, they ask us to find the area of region R. And so if we think about how we normally approach an area problem when the curves are defined in polar form, we take a little wedge of that region, and the wedge is always going to originate at the origin, and the outer edges of this little wedge are going to sit at the outer boundary of the region R, which in this case is f of theta. And so if we wanted to approximate the area of this one little wedge that I've drawn in blue right here, we can pretend that that wedge is a sector of a circle. It's not a perfect circle because we don't have a constant radius along the outer boundary here, but if we approximate that to be a sector of a circle, we can approximate its area with a quick calculation involving the formula for the area of a sector, which is 1/2 theta times r squared. Now if we make that more specific to the geometry that's established within our coordinate plane right here, we're going to have theta becoming some tiny range of values of theta, some tiny difference in theta. So the delta theta is going to become a d theta, the theta is going to transition to a delta theta when we're concerned with this little wedge right here. And then the radius is always along the curve r equals f of theta. So I've replaced the radius with f of theta, and of course that's being squared straight from out of the formula for the area of a sector of a circle. This expression right here will give you the area of one of these wedges. Well, we don't just want the area of one of these wedges, we want to add up the areas of a bunch of these wedges, and a definite integral by definition does just that. So if we use the definite integral to do the rest of the work, this is going to be our integrand. The delta theta is going to transition to a d theta in its limiting form. The limits of integration to trace out this stretch of that curve have to be 0 and pi by 2. If you toss that into a calculator and you see my TI-83 input right here, what you end up with is 0.648 square units for the area of region R. In part B, what they ask you to do is they ask you to consider array theta equals k. And it tells us that k is between 0 and pi by 2. And it divides the region S into two regions of equal area. So I went ahead and I drew this ray k into my coordinate plane. And I have this region of S that's up above the ray theta equals k. And I have this region that's below that ray, theta equals k. So I've got part of that region in red here. I've got the other half of that region in green. And what we're asked to do is we're asked to write but not solve an equation that has one or more integrals within it whose solution gives the value of k. So we want the region that's in red right here to be equivalent to the area of the region that's in green down below it. And so what I did is I handled the green region first, and I realized if I was going to go for the area of this region right here that I'm going to try to highlight with my green highlighter, that is going to be a calculation very similar to what we did in part A. I would have 1/2 delta theta times the outer radius, the outer boundary of any wedge that we took from what I just highlighted in green is going to be given by g of theta. Well, if we use an integral to add together a bunch of those wedges areas, we're going to have 1/2 g of theta quantity squared d theta, limits of integration. Well, theta right here is 0 and theta right here is k. Well, I wouldn't want the area that I've highlighted in green here. I'd want to subtract something off of that. And what I would want to subtract off of that is the area that I'm now going to highlight in yellow right here. So that is a region, a portion of region R. And so the area of region R, the integrand that we set up and established in part A, was 1/2 f of theta squared with respect to theta. Only change is we don't want the entire area of region R here. We just want the portion of region R as theta ranges from 0 up to Okay, so hopefully if you condense that to a single integral, 1/2 is a common factor, and then I'd have g of theta squared minus f of theta squared as the remainder of that integrand, and then the limits of integration were also the same, 0 to k for each. So this integral right here will give you the area that is in green, if I get all that highlighting off of it. And then we can do something similar for the area of the region that's in red up there. And it's going to be the same integrand. The only thing that changes are limits of integration. At this position on both g of theta and f of theta, theta is k. And at this position right here, to trace out these two sections of the curve, theta has to range from k up to pi by 2. So I have the same integrand, I just have different limits of integration, theta ranging from k up to pi by 2. Well, if I want to find what value of k makes those two areas have equivalent values, I'm just going to have to equate those integrals with each other. And that's exactly what I have here at the bottom of the screen back in blue. In part C, it tells us that w of theta is going to be defined to be the distance between the points with polar coordinates f of theta, theta, g of theta, theta. Write an expression for w of theta, and then it says let w sub a be the average value of w of theta on the interval 0 to pi by 2 and find what that value is. So here's what I did. I basically went through a derivation to convince myself of something. I realized if I'm looking for distance between 2 points, I can break out the distance formula from our regular Cartesian coordinate system. I also realized that if I'm trying to relate x with r and theta, x is always equal to r cosine of theta, and y, on the other hand, is always equal to r sine of theta. So I went ahead and figured out the x coordinates on my curves with that relationship, took their difference, squared it. Same thing with the y coordinates, r sine of theta minus a new r sine of theta for the difference between these two y coordinates here. I then realized I could do a significant amount of simplification with what's under that root. If I take this quantity here and factor out a cosine of theta, I'd be looking at this, and I factored out a sine of theta with the second term under that root. I then had a product here and a product right here, so I could square both pieces of that product. So that's what you see on this next line. Cosine squared theta times this quantity squared plus sine squared theta times that same quantity squared. Well, that quantity is the same on both this term here and this term here. So I thought, well, hey, why don't I turn this into a multiplication problem? Why don't I factor out this g of theta minus f of theta quantity squared from this term, leaving me with cosine squared, and this term, leaving me with sine squared. Well, if I'm adding together cosine squared theta plus sine squared of theta, what is that really? Well, according to the Pythagorean identity, that is just 1 right here. So that's 1. Well, if I have this quantity squared as the only thing that remains under the root, since I don't have to show that multiplication by 1, I can go ahead and take the square root of that quantity that's squared and end up with just g of theta minus f of theta. So if you were wondering where that relationship for w of theta came from, why it is as simple as it is, hopefully talking about some of the geometry and how the distance formula applies and simplifies is going to convince you as to why w of theta can be defined in this really simple way. So what is the average value of w of theta from 0 to pi by 2? Well, if you break out the formula for the average value of a function and apply it to g of theta minus f of theta and break out the calculator to do that integral, and again, you see my calculator input here, you figure out that the average distance between these two polar curves is going to be 0.485 units. And then in part D, they ask us to do a little bit more with what we just did in part C. So using that definition for w of theta in part C and that value that we found for w sub a in part C, the average value of w of theta on the interval 0 to pi by 2, find the value of theta when the function value for w is equal to that average. And so you do have to kick your calculator back to function mode in order to have it allow you to find an intersection. But what I did is I graphed w of theta, I graphed that constant value, what was it, 0.485? Is that what we got at the end of part C? Yeah, 0.485. and I figured out what that intersection was going to be. Now, one thing that I did here that wasn't the best thing to do, and I just didn't have time to go back and redo the calculator inputs before I put the video together. I should have taken all of the accuracy that my calculator provided me with back here. I basically should have stored that on the calculator. I do run the risk of a little bit of round off error based on the way that I handled the rounding off of this and just using 0.485 as the value that I graphed in this spot to go along with W of theta. I do get a value that's okay, accurate to the third digit beyond the decimal, but that was something that I basically ran the risk of losing accuracy with by not doing everything perfectly there. The intersection ends up being 0.518. So the value of theta that makes W of theta equivalent to its average value on the interval 0 to pi by 2 is about 0.518 radians. And then what we're asked to do in the remaining part of part D is decide whether the function W of theta is increasing or decreasing at this value of theta that we've just determined. Give a reason for your answer. So if you think about it, this is a pretty easy conclusion to build. If you find the rate of change of W with respect to theta at that value of theta, you can do that on the calculator. You just need the numerical value of the derivative and you get negative 0.581. I definitely can't keep the 0.581 and 0.518 apart from each other right now. My fault. But you end up with a negative is the significant aspect of this calculation. And why is that significant? Well, you know, if a rate of change is less than 0, you know the function that's the rate of change for is going to be decreasing at that moment in time, at that value of theta.